This video will review the subject of vector network analyzers, what they are, and how they can be used for measuring the characteristics of different components and circuit elements that we might encounter in amateur radio. So let's try to define a vector network analyzer. An Agilent tutorial from several years ago started with an optical lens analogy shown here. They said, "It is helpful to think of traveling waves along a transmission line in terms of a light wave analogy. We can imagine incident light striking some optical component like a clear lens. Some of the light is reflected off the surface of the lens, but most of the light continues on through the lens. If the lens were made of some lossy material, then a portion of the light could be absorbed within the lens. If the lens had mirrored surfaces, then most of the light would be reflected and little or none would be transmitted through the lens. This concept is valid for RF signals as well, except the electromagnetic energy is in the RF range instead of the optical range, and our components and circuits are electrical devices and networks instead of lenses and mirrors. Network analysis is connected with the accurate measurement of the ratios. Once again, that's the ratios of the reflected signal to the incident signal and the ratio of the transmitted signal to the incident signal. So let's first consider an instrument most of us have used or seen at some point in our amateur radio experience, the antenna analyzer. Here we're focused on the reflections we observe from an antenna and not the transmitted signal. Once again, the ratio of the reflected signal to the incident signal is important and defines a reflection coefficient called gamma. The voltage standing wave ratio, or VSWR, can then be calculated from gamma. There are two important things to note about the antenna analyzer. First, the incident and reflected voltages are usually not in phase, which means that the antenna is not a perfect resistance, but has a reactive component. Therefore, the antenna analyzer is capable of measuring more than magnitudes, but can measure complex impedances. The second important thing to notice is that the antenna only has one point of connection, namely the end of its transmission line. We can think of this electrical connection as a port. So an antenna could be described as a one-port network, and determining the VSWR could be called a one-port measurement. In general, networks can have more than one port, and we'll see that network analyzers are capable of measuring devices with two or more ports. A spectrum analyzer is a one-port measuring device that determines the magnitude of an input signal versus frequency within the full frequency range of the instrument. An optical spectrum analyzer could be a prism and a slit ahead of some type of optical detector. The prism and slit is basically a tunable filter that only passes one color or frequency of light. A radio frequency spectrum analyzer uses a tunable network that determines the resolution bandwidth of the analyzer. The results are usually shown on a display depicting magnitude versus frequency. Now suppose we add a signal generator ahead of the spectrum analyzer. If the signal generator is tuned to the same frequency as the filter in the spectrum analyzer, it is called a tracking generator. Now if we put a two-port circuit or network between the tracking generator and the spectrum analyzer, we can measure the network's transmission characteristics at different frequencies. In this way, for example, the response of a filter can be plotted. It's important to remember that only the magnitude of the transmission is being measured, so this type of instrument is sometimes called a scalar network analyzer. As a footnote to the tracking generator and spectrum analyzer measurement of the transmission characteristics of the device under test, let's take a quick look at how you can use the same instrument to make a one-port measurement of the return loss of the DUT, or device under test. This requires the use of a directional coupler, which attenuates the reflected power by a fixed amount. This fixed attenuation can be calibrated by first making a measurement with the device under test disconnected and thus presenting an open circuit with a 100% reflection coefficient. Once again, it should be pointed out that only the magnitude of the reflection is measured and not any phase information about impedance. In some cases, magnitude data is all that is required. However, in other cases, we need to have the phase information also. So we need to know whether we're dealing with inductance or capacitance in addition to resistance. Here is a block diagram of a vector network analyzer. There basically are two ports involved with the analyzer. A port which sends an AC signal to the device under test, and a port that receives a signal transmitted through the device under test. The first port is capable of measuring the reflected signal from the input of the device. The second port measures the signal transmitted through the device. It's important to emphasize that both the magnitude and phase of these signals are measured with reference to the incident signal. Then the analyzer processes the information and can present the measurement in terms of impedance, reflection coefficients, reflection loss, standing wave ratio, insertion loss, and in different formats such as linear and log plots or on Smith charts. So what type of devices and circuits might you want to measure with a vector network analyzer? Here's a list from the Agilent presentation and includes both passive and active devices. Some that might be familiar to amateur radio operators are filters, attenuators, duplexers, diplexers, splitters, and combiners. Some of the active devices, such as transistors, diodes, and amplifiers, may require more advanced vector network analyzers, but it's still interesting to know it might be possible to characterize these elements. Here is a picture of one top-of-the-line vector network analyzer, a Rohde & Schwarz ZVA40 that has 4 ports, which permits more complex measurements and simultaneous measurements. For reference, the price tag on this and similar instruments can be in the range from $100,000 to $200,000, depending on the options and accessories. Needless to say, as beautiful and desirable as they are, these are probably beyond the budgets of most amateur radio operators. Fortunately, there is a less expensive and alternative that may be of interest to the amateur community. In 2007, Professor Thomas Bayer, DG8SAQ, published his first article in the March-April edition of the ARRL-QEX magazine, in which he described his experiments with 2 direct digital synthesizer chips, a standing wave bridge, and 3 mixers to shift the RF down to the audio range where a PC and sound card could handle the analysis. This article was published in 2009 and represented a kit that was offered through a UK company called SDR Kits. Currently, SDR Kits is selling their 3rd generation of the Vector Network Analyzer, fully assembled with a calibration kit. More about that later. Unlike the first kits, which connected directly to the PC's audio connectors, the current versions attach to the Windows PC with a USB connector. Okay, it's time to dig a little deeper into the use of vector network analyzers, and we have to learn a little bit about S-parameters. We have incident and reflected waves at both ports of two-port devices. The incident waves are labeled A1 and A2, and the reflected waves are labeled B1 and B2. There are 4 S-parameters that connect these 4 waves. S11 and S22 are reflection coefficients such that B1 equals A1 times S11 and B2 equals A2 times S22. These reflection coefficients assume that there is no incident wave on the other port. Sometimes these reflection coefficients are expressed as a return loss, meaning that the incident waves are returned from the port at a lower amplitude than they arrived. S21 represents how much of the incident wave A1 is transmitted from port 1 to port 2 as B2. Likewise, S12 represents how much of the incident wave A2 is transmitted from port 2 to port 1 as B1. So, the wave B1 is comprised of 2 parts. That part which is reflected from the incident wave A1 through the reflection coefficient S11, and the amount transmitted from port 2 to port 1 from the incident wave A2 as measured by the S parameter S12. Although many of the measurements will involve these S parameters, you should also be aware that one can also define these traveling waves as voltages and currents. There may be some arbitrariness in these definitions, but these definitions simplify the expressions for forward and reverse powers in terms of the A's and B's. In order to use a vector network analyzer, we need to do a calibration. In addition, this calibration is made with respect to a so-called reference plane, which is usually at the end of the coaxial cable that connects to the input port of the device under test. We'll show an actual calibration later in the video, but let's go over the steps now. First, we put a short at the end of the TX cable. Next, we put an open circuit on the end of the TX cable. And finally, we put a 50 ohm load or resistor at the end of the cable. During these 3 events, the end of the RX cable has been open circuited. The final steps in the calibration involve connecting the ends of the TX and RX cables. In each of these calibration steps, the frequency of the vector network analyzer is scanned over the relevant measurement range. With the calibrations in hand, one is ready to measure the device under test. If you want to measure the device under test in both the forward and reverse directions, it must be disconnected and ports 1 and 2 must be interchanged. This brings us to the last topic before we look at some actual measurements. And this topic is called the S-parameter test set. Once again, that's the S-parameter test set. The test set utilizes a relay to automatically switch the TX and RX analyzer ports that are connected to the ports of the device under test. The test set then allows us to measure the device under test in both directions more or less automatically. Here is a drawing that demonstrates the switching. The coaxial relay takes special care not to introduce any impedance discontinuities that would influence the measurements. There is a website that has very helpful instructions for building an S-parameter test set for the SDR-Kit's Vector Network Analyzer. The link is http://k2gwk.com/sparameter.html. Here is the finished S-parameter test set using an SDR-Kit's Vector Network Analyzer version 3E. The coax cables are semi-rigid cables with SMA connectors that were purchased from Mini Circuits. The pilot lights on the panel show the user whether the sense of the TX and RX ports on the Vnwa are normal or reversed. Let's return for the moment to the topic of calibrating the Vector Network Analyzer. SDR kits can supply a calibration kit which comes in a small but professional-looking wooden box. These are all SMA connectors, and the next picture shows the 4 pieces in the kit. A male-to-male connector is in the upper left, a female-to-female connector is in the upper right, the 50 ohm load is in the lower left, and the short circuit connector is in the lower right. By the way, the actual resistance of the 50 ohm load is measured in a 4-point fixture, and in this kit is actually 48.78 ohms. In addition, Kurt Polson, OZ7OU, has put together a valuable information sheet to help the user with the calibration kit parts. Let's begin the calibration. In this case, we will be preparing the Vector Network Analyzer for measurements between 1 and 600 MHz. Note the test set light is green, which signifies that the relay is in the forward state. We start by connecting a short to the port 1 cable and starting the scan from 1 MHz to 600 MHz. Next, we connect the female-to-female SMA connector as the open connection and proceed with another scan. Now, we connect the 50 ohm load and scan again. This part of the calibration is finished by connecting the 2 cables together and initiating one more scan. Now we switch the test set to the reverse direction, and the red light is illuminated, indicating that port 2 will now serve as the tracking generator. The same procedure with the short, open, load, and through connections are repeated on the port 2 cable. As our first measurement, we'll start out with a simple case just to familiarize us with the display and to give us confidence that our calibration was valid. So our device under test is a 50 ohm, 10 decibel attenuator made by Mini Circuits. It is inserted between the 2 ports of the test set, and we start the measurements. All 4 S parameters will be measured in 2 scans. S11 will be shown on a Smith chart, and S22 will be shown as a plot of VSWR versus frequency. The transfer parameters of S21 and S12 will be plotted in decibels as a function of frequency. Now the test set reverses and the second scan begins. Notice that there are two transfer parameter plots near the top of the screen which overlay one another, which is good and shows that the attenuation is the same regardless of its orientation. Let's pause and look at the result. Remember, the frequency scan was from 1 MHz to 600 MHz. There are two markers shown here at 145 MHz and 445 MHz, and the values of the plots at these two frequencies are given in a table displayed at the lower left. Here is that information in a little larger type. S11 is displayed in the center of the Smith chart and is given numerically as the complex reflection coefficient, which is 0 plus I0. This confirms the 50 ohm value of the attenuator to 2-digit precision. S21 is 10.03 decibels and 10.02 decibels respectively at the two marker frequencies, and S12 is 10.05 dB at both frequencies. This is pretty good comparison between the two directions for the attenuator. Finally, S22 as measured in voltage standing wave ratio is 1.00 and 1.01 at the two frequencies. The values of these S parameters and the flat response over a 600 MHz frequency span is a very good result for this little attenuator. The next device we're going to measure is a DCI, Digital Communications Dual Bandpass Filter. This is a model DCI 145 435 dB and is a dual band filter intended to reduce intermod in the 2 meter and 70 centimeter bands. It is designed to be used with a dual band rig with a single feed line. The scan range is still 1 MHz to 600 MHz, and we'll select a VSWR presentation for the two reflection coefficients S11 and S22. The measure of insertion loss for S21 and S12 will be presented in decibels. We have markers at frequencies of 147, 223, and 444 MHz. The two bandpass ranges are quite obvious, and let's look at the four parameters at these three frequencies. S11 shows a VSWR of 1.52 at 147 MHz and 1.14 at 444 MHz. At the intermediate frequency of 223 MHz, S11 has a VSWR greater than 170. S22 is a VSWR of 1.51 at 147 MHz and 1.11 at 444 MHz. S21 is minus 1.11 decibels and minus 0.51 decibels at 147 and 444 MHz respectively, and S12 is minus 1.13 decibels and minus 0.53 decibels at 147 and 444 MHz. The transfer losses are in excess of minus 90 decibels at the intermediate frequency of 223 MHz. Now we're going to measure a 3-port device, namely a Diamond MX72N VHF-UHF diplexer. Since the SDR kit's vector network analyzer can only measure 2 ports at a time, the first question we face is what to do with the third port. The answer is to terminate it in a 50 ohm load. We'll make 2 forward scans, once for the VHF connection and the second for the UHF connection. In order to present the two scans on the same chart, we can take advantage of memories in the Vector Network Analyzer software. So we'll store S11 and S21 for the VHF scan in memories 1 and 2 respectively, and display these as voltage standing wave ratio and the insertion loss in decibels. Then we'll switch the test set port 1 to the diplexer's UHF connector and switch the 50 ohm load to the other side. The next frequency scan will show S11 and S21 for the UHF side along with the two memories to see the combined behavior of both the VHF and UHF inputs on the diplexer. Here we are seeing the second scan from the UHF connector. Note that the results of the VHF scan are already in place on the chart. Here are the results. At the VHF connector, we see that at 147 MHz, the VSWR is 1.06, and the insertion loss is minus 0.52 dB. But at the UHF connector at 147 MHz, the VSWR is 68.97, and the insertion loss is minus 60.29 decibels. At the UHF connector and a frequency of 444 MHz, the VSWR is 1.13 and the insertion loss is minus 0.46 decibels. And at the VHF connector at 444 MHz, the VSWR is 44.73 and the insertion loss is minus 57.53 dB. So we can see the diplexer is really doing its job. At the VHF and UHF frequencies, the VSWR is quite reasonable and the insertion loss is very low. And in addition, the isolation between the two frequencies is certainly greater than 57 decibels. Now we're going to look at a low noise amplifier from Down East Microwaves. It's a model L432LNA and uses an FPD 750 high electron mobility transistor made from aluminum gallium arsenide, indium gallium arsenide. This amplifier works from 420 MHz to 450 MHz and is rated for a gain of 17 dB. When measuring amplifiers, we have to be careful not to overload the RX port of the Vector Network Analyzer. So to compensate for the amplifier gain, we have reduced the output of the Vnwa tracking generator by 20 dB just to be safe. Also, the Vnwa has been recalibrated with this reduced output for a frequency range between 300 MHz to 600 MHz. Here's the start of the frequency scan, which will run in the forward and reverse directions, so we can see both the input and output impedances and reflection coefficients. S11 and S22 will be shown on a Smith chart, and the transfer parameters S21 and S12 will be measured in decibels. Note the origin of the dB scale has been moved slightly downward, since we expect both a positive value for S21 and a negative value for S12. One marker is at 381 MHz, which is near the peak of the gain, and the other marker is set at 444 MHz. S21 is 19.05 decibels at 381 MHz and 17.05 decibels at 444 MHz. This agrees very well with the 17 decibel nominal gain specified for the amplifier. S12, the reverse transfer parameter, is minus 38.08 decibels at 381 megahertz and minus 38.57 decibels at 444 megahertz. Not much of any signal injected at the output makes it back to the input. This is good because if it were not so, we might have an oscillator instead of an amplifier. Let's look at S11. At 444 megahertz, gamma is 0.43 minus I 0.62 and is equivalent to a voltage standing wave ratio of 7.1. This represents an input impedance corresponding to a 30.4 ohm resistor in series with a 4.1 picofarad capacitor. Next, S22, the output reflection coefficient. At 444 megahertz, gamma is minus 0.10 minus I 0.22 and is equivalent to a voltage standing wave ratio of 1.64. This represents an output impedance of a resistance of 37.4 ohms in series with a 20.5 picofarad capacitor. The software that is provided with the SDR Kit's Vector Network Analyzer includes the capability to analyze crystals and calculate a lump circuit model comprised of R, L, and C. One might be interested in this information if you were designing a crystal filter or a crystal oscillator. Here is a 12 megahertz crystal mounted in series between ports 1 and 2. The Vnwa is set up to scan 0.2 megahertz centered on 12 megahertz. The scan shows the transfer parameter S21, which has two sharp peaks. The one on the left is at 11.997 megahertz, and the one on the right is at 12.020 megahertz. We can now select the Crystal Analyzer tool in the software, and a new window opens. When the Auto Optimize button is clicked, the analyzer computes the values of the components in the equivalent circuit diagram. The computed values in this case are an inductance, L, of 18.70 millihenries, a capacitance C of 9.41 femtofarads, a resistance R of 10.73 ohms, and a parallel capacitance C0 of 2.44 picofarads. Interesting to note the calculated Q is over 131,000. If we go back and look at the scan of S21, we can see that the analyzer has added a computed plot of the equivalent circuit for comparison, and we can see that the two curves are in very good agreement. The Vnwa and its software can be set up to behave as an LCR meter and can measure complex impedance at a fixed frequency. Here is a toroid, and let's measure its inductance and resistance at 500 kilohertz. The answer is given for both a series and parallel arrangement for the inductor and resistor, with a Q of 4.53 shown here as approximately 5. The series circuit is an inductor of 8.47 microhenries in series with a 5.88 ohm resistor, and the equivalent parallel arrangement is an 8.89 microhenry inductor in parallel with a 126.4 ohm resistor. The last topic to look at is an example of time domain reflectometry. This can be a complex subject, so we'll just try to hit some of the important points. The basic idea is that if one were to send a very short voltage impulse signal along a transmission line, any impedance discontinuities would cause a pulse to be reflected back toward the source. This is demonstrated by the animation. Distance information can be inferred by measuring the time it takes for the reflected pulse to return to the source, much like a radar system. If a step change in voltage is created at the end of a transmission line, the amplitude of the reflected pulse can give information about the impedance change present in any discontinuities. The Vnwa is not capable of measuring these time delays directly, but it can measure the characteristics of a transmission line for different frequencies. It is an important engineering fact that a time domain response and a frequency domain response are related mathematically by something called a Fourier transform. We will look at a short section of unterminated RG6 transmission line 55 centimeters long. The response to a step change in voltage will be calculated from the frequency response generated by a scan from 25 kilohertz to 1.5 gigahertz using a discrete Fourier transform. Here is the scan with the S11 parameter plotted in decibels along the top. At the completion of the scan, the lower red curve will show the computed impedance plotted as a function of time or distance. The time across the bottom of the span is 5 nanoseconds, or a distance of 81 centimeters. Now we can see that the RG6 cable appears to be 75 ohms with a length of approximately 54.5 centimeters. Let's review what we've seen. A vector network analyzer is a piece of test equipment which delivers a sine wave with variable frequency to a device under test and can measure reflections from and transmissions through the device. The reflections and transmissions are characterized by S parameters in both magnitude and phase, which leads to information about complex impedances. The vector network analyzer can provide useful information about a number of passive two-port devices, such as attenuators and filters, and can characterize components such as resistors, inductors, and capacitors. Active devices such as amplifiers can also be characterized as long as care is taken to prevent overloading the network analyzer. Finally, the use of Fourier transform methods enables time domain reflectometry to determine transmission line length, impedance, and line anomaly some distance from the source. The demonstrations on this video were done with a PC-enabled vector network analyzer devised by Professor Thomas Bayer, DG8SAQ, and produced by SDR Kits.